Hello, my name is Mehdi and I will present our work, Reproducible Scale Laws for Contrastive Language Image Learning. I will start with an overview. So in our work we study clip scale laws on Lion, which is an openly available large dataset of image text pairs. With OpenClip, which is an open source replication of OpenAI's clip. For evaluation, we use zero-shot classification, retrieval, linear probing, and fine-tuning on multiple downstream datasets. In terms of findings, we identify a polar relationship between total compute and performance on downstream tasks, which allow us to do a prediction of model performance on larger scales. We identify bottlenecks when we restrict, for instance, data scale or sample scene. We also identify what we call task-specific scale laws, where we see an advantage of OpenClip line models on retrieval over OpenAI's clip models, whereas on the other hand, OpenAI's clip models have in general an advantage on classification tasks. So a bit of background, scale laws relate model performance and different aspects such as total training compute, dataset sizes, and models number of parameters. They are helpful for theoretical reasons to understand models' behavior on large scale, but also for more practical reasons to extrapolate model performance on large scale, larger than they have been trained on, for instance, to do experiment planning in advance. They can be used to compute the optimal model size and number of epochs to train on for a given fixed compute budget, which is often the case. They can also be used to compare different architectures, pre-trained datasets, or for instance, different kinds of losses in terms of their scalability to focus on the most promising ones. So there are existing works which show benefit of scaling contrastive language image training, but they are not done in a systematic way, often rely on private datasets and involve a customized training procedure, such as pre-training the image encoders. And so this is usually done in a different way in different works, which make it a bit difficult to disentangle the effect of scale itself. In terms of pre-training data, we use the OpenLarge Line 5B dataset. In terms of data scales, we use 80 million, 400 million, and 2 billion image text pairs. In terms of sample scene, we consider three scales as well, 3 billion, 13 billion, and 34 billion sample scene. In terms of model sizes, we use models ranging from 150 million to 1.4 billion parameters. We largely rely on the original OpenAI's clip work. In terms of model architecture, we add two additional model sizes, VIT huge, VIT giant, to train on larger models. In terms of evaluation, we use a set of 37 downstream datasets, which we use to evaluate the models on zero-shot classification, few-shot and few-shot linear probing, fine-tuning, and zero-shot retrieval. Here we show evaluation on zero-shot classification, where we identify a power law relationship between total compute measured in giga multiply accumulate operations and downstream error rate. This power law relationship translates into a straight line fit in the log-log space, which we show here for two example tasks. So in the left figure we show improvement with scale on ImageNet performance. In the right figure, we show improvement with scale on image robustness tasks, which are a set of 5 tasks that are usually used to evaluate robustness of ImageNet models to image distribution shift. So we see here also the scaling coefficients, which are quite similar between ImageNet and ImageNet robustness tasks, which shows that improvements in ImageNet are accompanied with improvement on related robustness tasks as well. We also identify bottlenecks when we restrict the pre-training data scale or the number of samples seen. So for instance here, when we vary the number of samples seen and restrict ourselves to the smallest data scale of line 80 million, we see that the performance saturates. Whereas if we use the largest pre-training data scale, we can see that the performance can still improve. Similarly here, when we scale the pre-training dataset, we see that when we restrict ourselves to the smallest sample seen, we can see that the performance not only saturates but can also decrease. Whereas if we use the larger sample seen, we can see that the performance can still increase. When we compare zero-shot classification and zero-shot retrieval results, we observe that OpenAI clip models have an advantage on zero-shot classification. Here we show ImageNet, whereas OpenClip Lion models have an advantage on zero-shot retrieval. Here we show COCO results. Since we use similar hyperparameters and architecture as the original clip work, we hypothesize this is due to the pre-training dataset composition. For instance, the web image text dataset that was used to train clip might have more affinity to ImageNet classes, whereas for Lion, we already know that it was pre-filtered using a clip model to eliminate noisy image text pairs. And this filtering might make it more suitable for retrieval tasks. In general, this hints to further research on pre-training dataset composition and filtering procedures and their effect on downstream tasks. We also evaluate the models on few and full shot linear probing and observe consistent improvement with scale. So in this case, we show few shot and full shot linear probing on ImageNet, and also full shot linear probing on VTab, which is a set of 19 tasks which include a variety of domains. Here we show fine-tuning results on image classification. We see again improvement with scale. In particular, we show here performance improvement when we increase the model size. Additionally, for fine-tuning, we had another setup where we first fine-tune on a subset of the full ImageNet 22K, which we call ImageNet 12K, which has 12 million examples. Then we fine-tune on ImageNet. Using this setup, we can improve the performance further. Finally, we use the power of it in order to extrapolate the model's performance on larger scales than what we have been training on. It can be helpful for experiment planning and to have an idea what to expect in terms of model performance. For instance, if the actual measured values are significantly deviating from the predicted ones, one could hypothesize that the training compute was not used in an optimal manner. That's it. Thank you for watching.